Okay, so good afternoon, everyone. Today I'm going to present a package that we are currently developing about advanced parallel random number generation in R. So let me start from where we started our journey into the parallel RNG world. Actually, we're facing a concrete Monte Carlo simulation problem where the key stochastic part of the problem was about simulating a matrix of random variables. In order to speed up the whole algorithm and to have a faster execution, we wanted to have a parallel implementation by splitting the different set of Monte Carlo simulations into subsets that would be executed on different processes. But we didn't only want to do this, but we wanted to have a parallel execution of, in general, a subset of the variable of interest. And a key requirement here was the fact that we would be able to simulate in parallel just a subset of the variables in a way that would be fully consistent with the sequential simulation to ensure 100% reproducibility. Well, if you want to do this, you have to face an intrinsic limitation in the way random numbers are generated. And this is because traditional random number generators are based on recurrences, which makes them intrinsically sequential. Still, in the context of parallel RNG, there are a few principles that you have to keep in mind. First of all, you want to have independent and non-overlapping streams in each of your parallel processes. But if you want to do one step further, you want to play fair. In this context, playing fair means that you want your results to be independent of the architecture, the number of parallel processes, and the technique you use to parallelize your algorithm. This means that you cannot really, you don't want to go for things like random seeding or having a different RNG per process, but you also want to avoid inefficient or naive solutions where you would always simulate the full sequence and just drop the draws that you are not interested in, or storing seeds for any possible thing you want to do. So in R, there are a few established packages that deal with the parallel RNG. In particular, the parallel package itself, the RStream package, and the rLecuyer package. But here the focus is mainly on non-overlapping and independent substreams. So that's how we came up with package rTRNG. So I assume we all know what the first R is about. So let me introduce you Tina's random number generator library. This is a state-of-the-art C++ library for sequential and parallel Monte Carlo algorithms. The library is developed and maintained by Heiko Bauke and is a broad collection of random number distributions and generators, or engines, as they are called in the library. With the rTRNG, we have brought all these to the R world by exposing the usage of distributions and engine into R, but also by providing the library itself and its headers to be available to other R projects using C++. So in particular, similarly to base R, you can draw from the distributions from the library using functions rdist in general underscore TRNG, where the engine argument would allow you to specify a specific random number generators that you want to use, and parallel grain can be used to enable a parallel simulation backend, which is based on RCPP parallel. For what concerns the engines, they are exposed to R as reference classes, and here we found RCPP modules as the easiest way to do that. And in particular, there are conventional legged Fibonacci RNGs and Mersenne twisters, plus a broad variety of so-called parallel-oriented RNGs. These are linear congruential generators, multiple recurrence generators, and yet another random number generator, which is basically a delinearization of a multiple recurrence generator. What makes the parallel engines so special? Well, they are based on linear recurrences. So they have a very simple structure, but despite this simple structure, there is a strong theoretical foundation about their statistical properties and how these survive transformations, basically. And the key part is that the mathematical structure, which is fairly simple, allows to manipulate them in a very efficient way. So how can I create, and manipulate an engine with rTRNG? Well, similarly to base R, you can select a global currently selected engine, and you can do operations which are very similar to base R, but you can also explicitly instantiate an instance of the relevant engine class and apply a set of methods. Now, if we ignore for a second these weirdly colored guys on the slide, we see that we can do what you would do in base R. So you can select the kind of the current engine, like a yarn2 engine. You can set the seed. You can draw uniform variates using it as a global engine. And then you can, similarly to .random.seed, extract the state and then restore it after having done some operations. And the same thing you can do if you manipulate explicitly an RNG engine object. So you can create it, seed it, pass it to rUnif TRNG, in this case, extract the state, and do things that you are familiar with in base R. In particular, since these are reference objects, it's very important to keep always in mind the difference between reference versus copy. So this is the way you would use, this is the conventional way of using random number generators in R. So all this is something that we should all be familiar with, but let's talk about what makes the parallel engine so special. Well, the first thing that you can do with the parallel engines is jumping. This is a very intuitive thing you want to do to be flexible and to be able to perform parallel, consistent simulations. So this allows you to advance the internal state of the generator by a given number of steps without having to go through all of the intermediate steps. This is possible for the parallel engines within the rTRNG package, thanks to the linear structure of the underlying recurrency. Because this allows to basically do this step operation in logarithmic time in the step size. So it's very efficient. So if we can go through an example. So we can create our yarn2 random number generator with a given initial seed, and we can use it to draw 15 random numbers. But what you can also do is, again, reset the same initial state with the seed. You can jump 11 steps ahead, and by doing this, we would be able to directly generate just the last 4 elements of the original sequence. So this is all very intuitive, and it is already quite powerful, and is also supported by some of the packages that are already available in R. There is a second technique, which is less intuitive but extremely powerful, which is called splitting. By splitting, I mean that we can generate directly a subsequence of the original one, where we basically skip every time, once we generate a fixed amount of elements. This is achieved by, in fact, calculating a new RNG, where the internal parameters are calibrated to generate the subsequence that we want to generate. So this is another example. In this case, using the global engine, again, of type yarn2, we set the seed, we draw 15 random variates, and now if we reset the seed and split the engine with basically saying that we want the 4th out of 5 subsequences, this allows to generate directly, without any extra generation time complexity, 1 element every 5, starting from the 4th. Now, if you put this in the context of our matrix of random simulated variables, this is basically what you want to do to simulate such a column. So this is something that you can do in R with the functionality that we have exposed to R, but you can also, in order to take full advantage of all these techniques, you can also have a project which is an R and C++ project, and for this, the library itself, the package itself provides the library and its headers. This means that you can very easily use source CPP to do some quick prototyping and have your standalone piece of code that uses these TRNG engines by just specifying the RCPP attribute depends with the package rTRNG. But you can, of course, then embed your own simulation algorithm that uses these techniques into a package where you have to specify the proper directives in the description, namespace, and make vars file. So here is an example of something that you could source directly with a source CPP. Again, maybe if you are not familiar with the CPP or RCPP code, in any case, you would recognize things that are similar to what we have exposed in R. In particular, we are creating a yarn2 object called RNG with a given initial seed. We can jump 15 steps ahead, and then we can split the same engine and start drawing from it. Now, if you look at this example and try to picture a bit what is going on here, we are in fact combining jump and split to take the full power of both techniques to do something like this. So in fact, if you have this picture of a matrix of random variables that you want to simulate, with jump, you can position yourself at the beginning of a given simulation that you might want to execute in parallel. And with split, you can select a given column that you want to start generating. This is, in fact, what I want to show as a last example. So this is basically what we started from in the first slide. So we want to simulate a matrix of IID normal random variables. And we want to do this in parallel, possibly selecting a subset of the variables. And we want to do this in a fair playing, so fully consistent way. And we want to do it regardless of how many parallel processes we want to have and which is the subset of variables that we want to simulate. It turned out that if we want to do this in the most flexible way, it's very easy to combine rTRNG with RCPP parallel. And there is a full vignette about this example where you can go and really see things in action. Here it is just, I want to just put on the key part of the RCPP parallel code. Here again, there is a lot about just RCPP parallel worker definition, which you might not be familiar with. But again, here you can see that you are splitting the full range of rows of the matrix. So this parallel 4 from 0 to m to the number of rows of m. And this you feed a parallel worker. So this will be done by RCPP parallel for you. What you in turn have to do is you have in the worker itself figure out where you are in the set of in the rows of the matrix. So this is this begin and end is the chunk of simulations you want to simulate. You have to make sure that you jump at the beginning of the first simulation that is assigned to one instance of the worker. And then for all the columns that you want to simulate, you can split the original engine to be able to simulate the corresponding subsequence. And this you do it for all columns that you want. And RCP parallel will make sure that all these covers split among different workers the full set of rows of your matrix. So to conclude, with package rTRNG, we have brought a state-of-the-art parallel RNG C++ library to the R community, where you can very easily experiment and prototype your own parallel algorithm that uses random number generators in R, using either the base R-like global engine functionality or by manipulating explicitly individual random number generator objects. But the full potential of these, we see the full potential of these as being used as part of other projects or packages that combine R with C++ and the TRNG library. The package is currently hosted on our GitHub repo, so you can go check it out. We would be really interested to see what is the interest around this topic. And you also find on our GitHub repo an applied example to credit default simulations, which we have in fact presented this year in Chicago at the R in Finance conference. Thank you.
All right, questions? Hi. So if I understand correctly, the actual random number generation is taking place in C++, and R is really like a wrapper around it.
Yes.
Is that true?
Yeah, this happens already in base R, actually.
Okay. So if I have different random number generation methods in C++, I can simply use all of them for this kind of random number generation in R, right? I mean, say if I have
other generators.
Sorry, say if I have a Merson Twister implementation in C++, or if I have a Witchman Hill implementation in C++, I can use the same functions.
Well, actually, you can use even something simpler, which is supported by base R. So you can provide, there is a standard interface for user-defined random number generators. Here, since we wanted to, in fact, be able to manipulate and create different objects, we went through a different path, but this is something that you can do and is supported by base R. If you want to just expose your own RNG implementation into R, you can do this, even without this package.
Okay, one other question.
Yeah.
So you talked about splitting, right?
Yeah.
So I have a different example for splitting. Say suppose if I had to draw 1,000 random numbers and I initially draw 500 and thereafter the remaining 500 I want to draw based on a condition. So if a condition gets satisfied, I want to draw the remaining 500. Yes. So how would I do that, preserving the stream?
Actually, what I've been presenting here and what the library itself provides are techniques for enabling fair playing parallel random number generation. Actually, in the end, if you have a specific simulation problem, you have to analyze it from a fair playing viewpoint and see how to use these techniques. So there is no general solution to any problem. So in the example that I mentioned here, you can see how we have tackled this for a specific application. If you have another application, you have to think about how to use it, which is always very good because with random number generation, thinking about them is always a good thing.
Okay, thank you.
Mm-hmm. Any other questions? Okay, let's